Well, welcome back. And our big topic tonight is to really discern the difference between even and odd functions and even and odd degree. And these are two topics that we seem to keep getting intertwined together, so our goal tonight is to straighten them out. So here's the rules you have to have memorized for even and odd functions, and functions being the key word. If a function is even, then it follows the rule. If f of negative x equals f of x, we call this function even. Odd follows the rule. If f of negative x equals negative f of x, we refer to it as an odd function. So let's go ahead and test a few examples. So is the function even, odd, or it doesn't have to be either, so we can say neither, even, odd, or neither. So let's say f of x equals x squared plus 3x plus 1. Okay, so the rule to test is, what's really nice about these rules is they both start the same. You're substituting in, if you look, at negative x. Okay, and then we just care what we get out. Do we get the original f of x out, or do we get a negative f of x out? So let's go ahead and see. So either way to test, I'm substituting in negative x, and every time I substitute, I'm going to use parentheses. So negative x squared plus 3 times parentheses negative x plus 1. Okay, and I'm just checking to see what I get out. So anytime I square something, we should know that comes out as a positive, so that's x squared, minus 3x plus 1. So now the question is, did you get the original, so it's even? Did you get a negative version, so it's odd? Or did you get a mixture and it's neither? Well, let's compare. X squared remained x squared, so at the moment it's the same, so I'm thinking even. But now the second one changed signs, so now I know it's not even because it's not the exact same, and I know it's not odd because this was positive and it remained positive. Therefore, this is a neither. Okay, so here's the rule, guys. When you substitute negative x in, either you get exactly the original, or you get the exact negated version of the original. Otherwise, it's nothing. Let's test another example. F of x equals x cubed minus 3x. Okay, and again, you do the same thing. You find f of negative x. Carefully substitute it in, and just see what happens. When I cube a negative, I now get a negative, so like a negative 3 times is a negative, and a negative 3 times a negative x is a positive 3x. So now compare this to the original f of x. Well, is it the same? Of course not. This changed signs. Is it different by a negative? Well, that means everybody changed signs. X cubed became negative, negative 3x became positive, so yes, this is an odd function. Okay, I'm not saying odd degree. I don't know anything about the end behavior. I just know that it's an odd function. All right, now let's take a look at a graphical approach. Sketch the other half of this graph, given that it's an even function. Okay, well, they're going to give me 3 points, and I just have to start with the rule for even. F of negative x, even and odd start the same, it's just what you get out, equals f of x. Okay, so how does that help you? Well, it's very simple. Let's say I take this point. So this point means f of 7 equals negative 2. So now it says take the x value and make it negative. So f of negative 7 also has to equal what f of x is, what the y value is. It also has to equal negative 2. So I now can plot the point negative 7, negative 2. Okay, so we'll do it with this point, 3, 5. So they're saying f of 3 equals 5, and the rule says if I negate the x, so f of negative 3 also has to equal 5. And I can do one more here, f of 0 equals 0. If I negate 0, I still get 0, so that's the point 0, 0. And you can see, we can sketch the rest of the even function. Now, what do we have to know about even functions? Well, this picture says it all. It's symmetric to the y-axis. So let's go back and get a big star there, and an even function, it has symmetric to the y-axis. Okay, so let's take a look at a second graph. This time they're telling me it's odd, and we're still going to do the same rule. We're going to use the odd rule. F of negative x, now this time it's equal to negative f of x. So let's again take the point 7, negative 2. They're really saying f of 7 equals negative 2. So if it's odd, it says if I negate the x, this time I have to get out negative f of x. So I'm not going to get negative 2 back out, I'm actually going to get positive 2. I have to take the f of x value and make it negative. So if it's already negative, it becomes a positive. So I'm going to graph negative 7, positive 2. Okay, so let's say if f of 3 equals 5, the rule says f of negative x is going to equal negative f of x. So now I'm going to get negative 5. So I'm going to go over negative 3 and down 5 at that point. And f of 0 equals 0. If I negate 0, I still get 0. And now you'll see the odd function. So now the odd function, what is that symmetric to? Okay, and it's actually, let's put a big dot here at the origin. That is what it has symmetry. It's symmetric to the origin. So again, I would get that starred. An odd function is symmetric to the origin. Okay, now graphically, what that basically means is if you flip this paper upside down, if you take your notebook, flip it upside down, you should see the exact same picture. All right, so the question is even, odd, or neither. So again, when I'm given the function, I'm going to test it with the rule. F of negative x, and I'm going to see what I get. So I get negative x plus 4. So I'm saying, okay, did it stay the exact same? Well, of course not. I have a positive x here and a negative x here. Did the whole thing change signs? Did this become negative and this become negative? No, so I'm going with neither. Guess what else you could do, guys? You have a graphing calculator. Could you all graph x plus 4? And I believe it looks like this. So I can clearly say this is not symmetric to the y-axis, and if I flip it upside down, respect to the origin, it's not in the same position. Okay, let's try g of x equals 3x squared. Well, g of x equals 3x squared. So I'm going to test my rule. I'm going to substitute in negative x and see what I get. 3 times negative x squared is equal to 3x squared. This function stayed the complete same. Therefore, that is the rule for even. Now again, guys, you have a graphing calculator. Let's say you forget the rule on the test. Could you just graph it? Of course. 3x squared looks like this, and you can clearly see it's symmetric to the y-axis, hence even. The third example, so I have a picture, so I'm saying is it symmetric to the y, the origin, or neither? And hopefully you're saying it looks even, symmetric to the y. And then k of x, my last example, clearly it's not symmetric to the y. If I fold right on this line, it does not land on top of each other. Origin, well, flip it upside down, and if it looks the exact same, it's odd, and it does, so I'm going to go with my odd function. All right, so go ahead and copy down this table here, and we will fill it out together. Given the partially filled out table below, for the odd function, fill out the rest. So again, that keyword is odd, and if you don't know the rule, this is pretty impossible to do. So remember, f of negative x, they both start the same way. If it's even, we get f of x, and if it's odd, we get, hopefully you've said it, negative f of x. Okay, so let's take a point that we know. We know f of 2 equals negative 3. So if f of 2 equals negative 3, when I substitute in negative x, I have to get out the opposite answer. I have to get out negative f of x. So I don't want a negative 3 for my answer. I'm actually going to get out a positive 3. So I now can fill this piece out. At negative 2, I should be getting a positive 3. Let's take another one we know. F of negative 1 is equal to negative 7. And the rule says when you substitute in negative x, so in this case that would be 1, I need to get out negative f of x. So I should get out positive 7. Okay. And then the last one, f of negative 3 equals 6. When I substitute in that negative x, so it's going to get me f of 3, I need negative f of x out, so I need out negative 6. Now, could you also plot those points? Of course. And this time, because it says odd, remember, you want to make sure it's symmetric to the origin. Okay, and those O words kind of go together, odd and origin. So let's go ahead and do a similar one, even. So I'm going to take a point I know, f of negative 3 equals 6, and the rule says when you substitute in negative x, so that would make that a positive 3. So Let's write that rule down. F of negative x equals this time f of x. So I should get out the same thing, positive 6. F of negative 1, it says, equals negative 7. So when I substitute in negative x, so positive 1, I need to get out the original f of x. And what else do we know? F of 2 equals negative 3. So when I substitute in negative x, I need the original out, so it's going to also equal negative 3. Okay, and again, if you were to plot these points, so what do we have? 0, 0, at 1, negative 7. I better have symmetry, so at negative 1, it also better be negative 7. Okay, and again, that's that whole symmetry idea. Of course, when I plug in 2, I should get negative 3. So when I plug in negative 2, I should also get negative 3. And when I plug in 3, I should get a 6, and negative 3 is 6 as well, and there's our symmetry. Okay, so now switching gears completely on you. There was even and odd functions, and now notice this big difference here. This is even and odd degree. And what is a degree? Well, if I say f of x equals x to the n, the degree is the nth power. Okay, so now we're talking about the degree, not symmetry, so to speak. So let's talk about what we know. Let's take two easy ones. What if I said f of x equals x squared? Is that something you can picture in your head right away? I hope so. I hope you're all picturing the shape, so to speak, of a parabola that's opening upwards because it's a positive. Okay, so what does that tell me? Well, if this exponent here is even, notice the end behavior. This goes up to infinity, and this goes up to infinity. Basically, they're going to the same spot. Now, why are they going to positive infinity versus negative infinity? Well, that tells me the coefficient here. Okay, so let's make a few notes here. If the exponent is even, okay, the end behavior is the same direction. Okay, so if I said x to the 6, you also should be picturing the end behavior at the ends either going both up or both down. They go in the same direction. Now, what tells it to go up versus down? Okay, so now you need to pay attention to the coefficient, which of course just means the number in front of, so jot that down if you need to, the coefficient of the largest term. Okay, so, and I think it's really easy. I picture positive x squared. If it's positive x squared, both of the ends are going up. Where I think this is also easy. Can you picture negative x squared in your head? Okay, so again, it's even, so let's box that in. It's even, so we know they're in the same direction. But negative x squared is the frowning or upside down parabola. And because the coefficient is negative, the end behavior is pointing down. Okay, so I hope you can make that connection. Let's talk about an odd degree. Okay, so again, the one that pops in my head right away is f of x equals x cubed. Okay, now if that's not a common graph you know, it needs to become one. That is one of the few common graphs that you are responsible for on our Common Core, and actually you were in Algebra 1, and now it happens again in Algebra 2. So you should be able to picture x cubed in your head. It starts low and it ends high. Okay, so again, when this is an odd degree, notice the end behavior goes in opposite directions. Do you love how all these O words connect? Okay, when it's an odd degree, the end behavior goes in opposite directions. Now, what tells it, where to start and where to end? Well, take a look at x cubed. If this is a positive, it actually starts low, but ends high. Okay, likewise, if I said f of x equals negative x cubed, looks like this. And again, if you forgot, could your graphing calculator tell you that? Of course. So you'll notice that it's odd, so they go in opposite directions, but the negative tells me to start high and to end low. So let's take a look at our first example. It says, which of the following graphs best illustrates y equals a x minus b squared times x minus c, where a is less than 0 and b does not equal c? Wow, that might sound like a mouthful to you, but there's a lot of important information going on. First of all, they're telling me the coefficient, that a value, is a what type of number? Negative. Good. So basically, I'm just going to put a negative a there because I know that that's a negative value. Now they tell me b cannot equal c. Now, why is that important? Well, if these are different numbers, then they have to have different zeros. So they can't be the exact same. Okay, so I have to have a b for a 0 and a c for a 0. So how many zeros do I have? Let's start with that. Well, I have b and I have c. I would say I have 2 zeros. So to me, I think this graph is out because it only has 1 0. And I think this graph is out because it only has 1 0, where I know I have a b and a c. Okay, now, this graph has 3 zeros, this graph has 3 zeros, and this graph has 2 zeros. So right away, my gut's leaning towards this one. And now let me verify some other things. If I were to FOIL this out, okay, so y equals, we're going to call it negative a, times x minus b squared times x minus c. Okay, what do I know? I know that this biggest term is going to be x squared because it's getting squared, and I'm multiplying it by an x, which should give me an x cubed. Now that degree is odd, which tells me the end behavior has to go in opposite directions. Okay, so again, that guy's out because it's going in the same direction. That guy goes in opposite, that guy goes in opposite, and that guy goes in opposite. The other big thing now is that this is negative, so I know it's going to start high and end low. Now again, let's just say you completely forgot that, okay? Basically, guys, what you have to be able to do is make up your own letters for A, B, and C. Could you pick any number you wanted where A is less than 0? Let's say you type in your calculator y equals negative 2. And now you pick a value for B and C that aren't the same. Maybe x minus 1 squared and x minus 4. Who knows? Okay, could you graph that and say it looks closest to the shape of this? Okay, that would be another way to handle this. Now, I forgot to talk about one of the most important things. When I see this squared term here, okay, you probably need this in your notes. Remember, there's a bounce in its step. So if I look, it should bounce right where B is. It shouldn't go through. At x equals c, the graph should go through as a 0, but at b, because it's a squared, it's going to bounce, that even exponent. Okay, next example, which of the following best illustrates this graph? And again, they're telling me a is a negative number, and b, c, d, and e are not the same. They are all different. Okay, so the first thing I say is how many zeros do I need? Well, that's 1, 2, 3, 4, and they all have to be different. So who's out? That guy only has 2. This guy only has 2. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. That guy's out. So right away, I've narrowed it down to 2 functions. Okay, so now I'm going to say, is it even or odd? Well, I have x times x times x times x. That's 4 of them. That's x to the 4th. So I know it's even. So the end behavior should be the same. And now I need to say a is negative. So in my head, I'm picturing like negative x squared. What does that look like? Well, that means they both start and end low. Okay, now let's go ahead and watch the notation. We're going to say as x approaches positive infinity, so as the x-axis goes out to positive infinity, the graph is headed towards negative infinity. F of x approaches negative infinity. Let's say as x approaches negative infinity, what is f of x approaching? Okay, so if you go out forever on the x-axis in the negative direction, where is the graph approaching? Negative infinity. Good. All right, let's tackle another one. Which of the following best illustrates the graph? Okay, so again, I should have a 0 of a B, a C, and a D, and they're all different, so I should have 3 zeros. So let's eliminate anyone we can. So 1, 2, 3, 4, that guy's out. 1, 2, 3, 4, 5, that guy's out. 1, 2, that guy's out. That has 2, 1, 2, 3, this guy has 3. So now just based off that, that was a lucky choice. Let's kind of be real careful here. And here's what you have to get out of this tonight. We have to remember this. Okay, because this is being squared, it has to bounce. B-O-U-N-C-E. It has to have a bounce to it. So I know this is where the D value is because it bounces at D. Whereas it goes through at B and at C, it bounces back at D. Okay, so again, I narrowed it down just based off the zeros, but I know it has to have a bounce. And then they told me A was negative, which means my end behavior has to be the same. So let's just write the end behavior out. So as x approaches positive infinity, f of x approaches. So if I go forever on the x-axis, this height is forever going down, negative infinity. As x approaches negative infinity, f of x approaches. If I go this way forever, the graph is always going down. All right, so one more. Now this one's a little sneaky. I've got x minus b and x minus c cubed. So I know I have two zeros. I have b and c. Now notice it's not squared, so I'm not looking for a bounce because it's not even. Okay? This time, we like to call this a saddle. Okay, can you picture a horse saddle? That's what we're looking for. Okay, not a bounce, but a saddle. So, let's first decide if we have an even degree or odd degree. So I have x to the third times one more x. So I'm going to say that's x to the fourth. So remember, I can have at most 4, but I know I have just 2. So let's eliminate somebody. That guy's out, that guy's out, that guy's out. Both of these have just 2 zeros. Now, do you see what I mean by saddle? Notice here, it didn't bounce, and here it didn't bounce. It's kind of like a horse saddle. It goes down and up. A little horse saddle is what we call that. So I know I have a saddle, and now the only difference is that this end behavior is down, whereas this end behavior is up to infinity. So it all depends on that a value, and that a value is negative. So again, I'm kind of picturing like negative x squared in my head saying, okay, that end behavior has to be downward. Okay. Well, hopefully this kind of clears up the difference between even and odd functions versus even and odd degree. Expect a quiz tomorrow, and we'll see you then.